This is Jack Jackson. In this video, we're going to be talking about the derivatives of the inverse trigonometric functions. So we're going to derive the formulas. And actually, you can see the formulas in this box here. Now, we'll come back to that. It's kind of interesting, I guess we might notice right off the bat, that the derivatives of the inverse trig functions actually are algebraic functions that do not involve trigonometric functions or inverse trigonometric functions in their final versions, which is kind of a pretty cool result there. Now, before we do this, we need to remember the inverse function rule. And so we're going to use this rule. We derived this earlier. You might go back to our earlier video and recall what's going on here. But the derivative of an inverse function is 1 over the derivative of the original function evaluated at the inverse function. We're going to be using that and then the derivative rules of the 6 basic trigonometric functions and then some other manipulations to help simplify these things. So let's jump right in. Now, I guess the first thing we should remember is what is an inverse trig function? Sine inverse x, or I'd prefer to say arcsine of x, which is I think a better way of writing it. I've written it more the way I wrote it this way because most of the calculators use this notation here. But I really prefer the arcsine, arc, cosine, and so forth version, because any other number you put it right here, it means a power. But -1 put there does not mean a power, does not mean a reciprocal. If we had sine to the -1 power, we would just write that as what? Cosecant of x. Okay, but a -1 here means an inverse function. It means arcsine. So what that means is we take the x and y on the sine graph and switch them, but we don't do it for the whole thing, because if that were to happen, we get a wave going all the way up and down. We want this to be an actual function. Well, every relation has an inverse, but its inverse may not be a function. The relations where both the relation and its inverse relation are both functions are actually one-to-one functions. So what we have to do is we take the sine, we restrict it down to a smaller domain, we take the inverse of that, which is the arcsine. So the arcsine is not, technically speaking, really an inverse of the sine function, but rather an inverse of the sine with a restricted domain. So as long as we stay in the right parts here, the right x and y window, you might say, then these are inverse functions of each other. So the blue one is what we get for the arcsine function. Now let's just kind of take a look at that. Notice that it increases from a -1, comma, negative pi over 2 to 1 comma pi over 2. It goes through the origin. It increases the whole way, so its derivative should be positive, which you see it up here. The first part is concave down when x is negative, and so that means the derivative is decreasing when x is negative. And the original function is concave up when x is positive, which says the derivative is increasing. The origin is also an inflection point, so when x is 0, the derivative has a minimum. So this is what the derivative should look like. Notice that the arcsine function, or inverse sine function, is only defined from -1 to 1 inclusive, and so its derivative is only defined there as well. And in fact, the derivative is actually undefined at the endpoints, because the endpoints would, if you continue this on, would have a vertical tangent line. And so the derivative is approaching infinity on both sides here. And so it's only defined from -1 to 1 open interval for the derivative. Okay, so let's take a look and see if we can now actually derive the formula for this red function, which is the derivative. Okay, so here we are using the inverse function rule that we have right here. This is 1 over the derivative of sine of u, but we evaluate it where u is the inverse sine of x. That's how the inverse function rule works. So the derivative of sine of u is cosine of u, but then we plug in inverse sine. Now at this point, it looks like we have an answer, but it's involving inverse sines and inverse trig function and a trig function. But if you have the inverse trig function in the middle, and then the outside you have a regular trig function, it turns out you can reduce that. So let's take a look at this. Now remember, the inverse sine or arcsine of x is an angle. We're going to interpret that as an angle. And so think about putting that angle here. Now the inverse sine of x, it's going to be the output of this, which is actually an angle between minus pi over 2 and pi over 2. So it's a sine, it's an angle where you put it in the standard position. It's either going to be a first or a fourth quadrant angle. So I've got it kind of drawn as a first quadrant angle. Now let's put this inside of a unit circle, and so we have a radius of 1 here, and we make a little right triangle. Now we know that the sine of this angle is going to be x. So the inverse sine of x is an angle whose sine is x. Well, in a triangle here, the sine is the opposite over hypotenuse, so that's x over 1. Now using the Pythagorean Theorem, we can find the other side here. So 1 squared minus x squared is going to be this side squared. So this side is the square root of 1 minus x squared. So I use the Pythagorean Theorem to come up with this radical down here. Now what are we wanting? We're wanting the cosine of this arcsine of x. So we want the cosine of this angle. Well, the cosine of this angle is adjacent over hypotenuse. And by the way, whether this is pointing up or down, it doesn't matter whether this x is positive or negative. We're still going to square it here, and so it's going to work out. And so we do that. Now, to check this, we could check it like we do all of our functions with the calculator, but we can also check it by graphing. And you could try to graph it and see that it works out like this, and it seems to have the appropriate features, the appropriate domain and range that we need. Notice that if x is 1 or negative 1, then this becomes the square root of 0, which is 0. We've got 1 divided by 0 is undefined. That's where your vertical asymptotes happen. If you're between 0 or between negative 1 and 1, when you square that, you get a number less than 1. 1 minus that's a positive number, so this thing is defined. If you're bigger than 1 or less than negative 1, when you square that, you get a number bigger than 1. 1 minus that will be negative. This becomes an imaginary number, and for our purposes here, that's not defined. All right, does that make sense? Hopefully that does. Let's do inverse cosine. Now the arc cosine or inverse cosine is going to be this blue function right here. Notice that it is defined between negative 1 and 1, just like the sine is. But this time the y values are between 0 and pi, whereas the y values on the arc sine were between minus pi over 2 and pi over 2. In other words, the angle that you get out of it, the y value over in this picture is an angle on, let's say, a unit circle picture. And so the angle on the unit circle picture is a first or fourth quadrant angle for arc sine. But for arc cosine, it's a first or second quadrant angle, an angle between 0 and pi inclusive. So it has solid endpoints here and here. Here that starts over here at the upper left at negative 1 comma pi. It just decreases down to where it hits the x-axis at 0 comma pi over 2, which is an inflection point as well. And then it continues to decrease on down to 1, 0. Notice that this cosine, inverse cosine, decreases the whole way, so its derivative will always be negative, which is their derivative is the red graph, so that makes sense. It's going to be, it has an inflection point at the origin, so that's going to be our maximum here on the derivative. The original function is concave up when x is negative, so that says that the derivative is increasing. And the first function, the original function, is concave down when x is positive, and so it says the derivative is decreasing. So this the graph shapes appear to work correctly here. Okay, now let's actually derive the formula for that red graph. Okay, very similar manner to what we did over here for the derivatives of the arc sine. You take the derivative, it's 1 over the derivative of the cosine, the inverse function of this. These are inverse functions if we restrict our attention to the right x and y ranges there. Okay, so this is 1 over the derivative of cosine of u, but you evaluate that at u equals cosine inverse of x, or inverse cosine of x. So the derivative of cosine u is the opposite of sine of u. Plug in u is inverse cosine of x, and we get this. So it's minus 1 over sine of the inverse cosine of x. Now, this time when we draw our triangle, the inverse cosine should be a first or second quadrant angle. I've got it drawn out at least for the first quadrant angle. And you draw in your reference triangle here. Now, this angle is an angle whose cosine is x. So if you remember, cosine is adjacent over hypotenuse, so we put the x down here and the 1 here. We see that the cosine of this angle is in fact x. Then we use the Pythagorean Theorem to get the other side, which is the square root of 1 squared minus x squared, or the square root of 1 minus x squared. Now what do we want? We want the sine of that inverse cosine, the sine of this angle that's down here in the lower left corner. So that's going to be opposite over hypotenuse. That's the square root of 1 minus x squared over 1, which is the square root of 1 minus x squared. We still have this minus. We still have this minus out front. We still have the 1 on the top. So it's minus 1 over this square root. If you graph that, you get this red graph here. Okay, let's keep going here. Inverse tangent is this blue one. Notice it goes from minus infinity to infinity for the domain, but the range only goes from minus pi over 2 to pi over 2, which are horizontal asymptotes on the left and right, respectively. Notice that the inverse tangent function is increasing the entire way, so its derivative will always be positive. You notice the red graph is always above the x-axis. Since it has horizontal asymptotes on both the left and right, as you go out to the extremes, the graph of the inverse tangent is getting closer and closer to being horizontal. That means it's getting closer and closer to having a zero slope, so its derivative must be getting closer and closer to zero. In other words, the red graph, the derivative graph, must have the x-axis as a horizontal asymptote, which you see it does. For the negative x's, notice that the arc tangent is increasing, and well, it's increasing everywhere, but it's also concave up. So that means the derivative is going to be increasing. But for the positive x's, the arc tangent is concave down, so the derivative is decreasing. So the derivative actually has a maximum at 0, okay, 0, 1, I believe, yeah, 0, 1, and that's going to be where the arc tangent has the inflection point there at the origin. Okay, so you can kind of see what kind of a shape we're dealing with. Okay, let's derive the formula. Very similar to what we've done before. The derivative of the inverse of the tangent of x is the derivative of the tangent of u evaluated at the inverse tangent. Derivative of tangent is secant square of u, but we let u be inverse tangent. Okay, so now let's take a look at this. We think of an angle here, and by the way, it's an angle between minus pi over 2 and pi over 2. Okay, think of a unit circle picture. That's a fourth or first quadrant angle. And this angle is going to be represented by this angle in this triangle. Now we know the tangent of that angle is x. So that's opposite over adjacent is x over 1. So if we let this opposite side be x and the adjacent leg be 1, then we have the correct ratio there. Now we use the Pythagorean Theorem to find the other side, the hypotenuse. So it's x squared plus 1 squared is the square of the hypotenuse. So the hypotenuse is the square root of x squared plus 1. Now, what we want is the secant square of this angle. So this is our angle down here. The secant of that angle, now let's see, remember, secant is reciprocal of cosine. So cosine is adjacent over hypotenuse. So secant is hypotenuse over adjacent. So the secant of this angle would be square root of x squared plus 1 over 1, or in other words, the secant of this angle is the square root of x squared plus 1, but then we want to square that, and so we get x squared plus 1. Now that's in the denominator, so the derivative is 1 over x squared plus 1. if you graph that, then in fact you do get the red graph. Now I encourage you to check all of these problems by the way we always check our derivative problems, with our calculators. In fact, let me maybe we'll do one of these in a minute. Okay. Okay, let's clear out some things here. So for example, we could check this one. If you let y1 be the inverse tangent, okay, first of all, make sure you're in radian mode, which we are. Okay. Next, let y1 be the inverse tangent of x. Let y2 be, let's turn that off, but leave it in there. Let y2 be the numerical derivative of y1, like we usually do. And then put our answer, which is 1 divided by x squared plus 1. Now let's look at the tables for y2 and y3. And let's make sure we check some negative and some positive stuff. Yeah, that looks pretty good, right? And so this gives us a little bit of a check. And look at the table. There we go. All right, and so that seems to check out quite nicely there. You know what? While we're at it, let's just go back and check the ones we've already done before we go any further. So we did 2 on this page. Let's check those as well. So this is inverse sine of x. We do the symmetric difference quotient, or numerical derivative, there. And our answer was 1 over square root of 1 minus x squared. 1 over square root 1 minus x squared, close the square root. That should work. I don't need to see y1, so let me just look at that. And look at the table. Okay, notice they gave us a lot of error messages. This thing is only defined between -1 and 1. So, well, it worked at 0, but that's not really much of a check. So let's go back to our table setup. Let's maybe start at, well, -1's even an error, but let's say negative point. Negative 0.3 going up by 0.1s automatically, and then look at a table. There we go. That's a better check there. Okay. Alright, give me just a second to kind of get this where I want it to be. Alright, we're getting there. Okay, well, that one checked out nicely. Okay, now let's see if we can check this one. Okay, So this is going to be inverse cosine of x. So change this to arc cosine of x. And this one is, okay, supposed to be, let's see. So if you look, it's kind of interesting. It's almost the same formula. This one just has a minus in front of it. Okay. And I don't need to see the table for y1. What I need to do is see the table for y2 and y3. Alright, let's look at the table. Let's see if it checks. Again, I need to mainly look between -1 and 1 because if you get to -1 or beyond, to the left or to the right of 1, the whole thing is undefined. It's definitely good to check both some positive and some negative values when you're checking these, just to make sure there's not some kind of technical issue that we're missing. Alright, so those checked out just fine. Okay, now let's go to this one. Inverse cotangent of x. Now, Graphmatica that I've been using to do these graphs actually does inverse cotangent incorrectly for the way I define it in my trig classes and in my calculus classes. The way I define inverse cotangent, I want it to be one connected piece. Okay, and so for that to happen, this is what the graph looks like. And so the outputs of the inverse cotangent are between 0 and pi. In the unit circle picture, that's a first or second quadrant angle. And notice it has asymptotes of negative, as x goes to negative infinity, the asymptote is pi, and as x goes to infinity, the asymptote is 0. And again, since it has horizontal asymptotes, then the derivative is approaching 0 on both ends, so it has an asymptote there. Notice that the way this is done, it's one connected piece, so the derivative is defined, well, it's continuous, but not only that, it's smooth everywhere, so the derivative is defined everywhere. And the derivative will always be negative because the original function is decreasing, and you can see that works for the function that I have graphed here. Let's see, when x is negative, the arc cotangent function, or inverse cotangent function, is concave down, so the derivative is decreasing. When the x is positive, the arc cotangent function is concave up, so the derivative is increasing at x equals 0. And by the way, y is pi over 2 in the original function. The slope there is actually -1, and so that's where we have a minimum of 0, -1 on the derivative. So this is what we have right here. All right, let's get the formula for it. Well, using our little rule that we've been using, the derivative of inverse cotangent of x would be 1 over the derivative of cotangent of u, but evaluate at u equals cotangent inverse of x. So derivative cotangent of u is minus cosecant square of u, but the u is inverse cotangent. Okay, so notice we do have a -1 here. And then we have, turns out we're going to have x squared plus 1. So this one, cotangent and tangent, are the same with just an opposite sign. Okay, and so let's take a let's take a look at that. Okay, so again, if we let this angle, inverse cotangent of x, be the angle here in our right triangle, this is an angle whose cotangent is 1. So that's x over 1, that's adjacent over hypotenuse. Tangent is 1 over x, the cotangent is x over 1. Using Pythagorean Theorem, the hypotenuse then has length square root of x squared plus 1. What do we want? We want the cosecant of that and then square it. Cosecant of this angle. Cosecant of this angle is 1 over the sine. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So it's square root of x squared plus 1 over 1, which of course is just square root of x squared plus 1. But then we have that squared, so that cancels the square root, leaves in the denominator x squared plus 1. I move the minus from the denominator to the numerator, and we get that. And once again, you could graph that and see that it works out the way I have this defined. This one's a little harder to check in the calculator because you may not have an inverse cotangent button. Okay, so I'm going to just leave that for now on the check. Okay, let's do the last two. The derivative of inverse secant of x is 1 over the derivative of the secant of u, evaluated at u equals inverse secant of x. Derivative of secant of x, secant of u is secant u tangent u, but u is inverse secant. Alright, let's look at the picture. Inverse secant is here, is the angle. The secant is the hypotenuse over adjacent, so that's x over 1. X is the hypotenuse, 1 is the adjacent side. Pythagorean Theorem gives you the other side, which is x squared minus 1 squared, square root. So it's the square root of x squared minus 1. Now what do we want? We want the secant of this angle. Well, the secant of this angle, of course, is just x. The secant and the arcsecant cancel each other out, leaving x. Or from this picture, it's hypotenuse over adjacent. Now we also want the tangent of that angle. The tangent is opposite over adjacent, so that's square root of x squared minus 1 over 1. And so this tangent of the inverse secant becomes this square root right here. And this is what we get for our graph. The blue graph's the original one, which is in 2 pieces here. There's a little gap here in the middle. They both have the same horizontal asymptote of pi over 2. This one has a nice little endpoint of -1 pi, and this one has an endpoint of 1, 0, and then they go on out like this. Notice that both pieces where something doesn't look quite right here. Okay, this is not quite right if you look at the picture, because if I've got the right thing graphed, let me go to Graphmatica and I'll actually graph this in just a minute. So let me go to Graphmatica. Let's start by graphing y equals a secant of x. Okay, it does that one correctly. Let's make that the original graph blue. Let me see if it should just graph the derivative. Yeah, that's what the derivative should look like. So what we need in this one here, we have to be a little careful. We need absolute value right here to get it to work out right when it's negative. I believe that will fix our problem. Okay, so when x is negative, we get that. So notice, let's see if that works out right now. So that function is supposed to be 1 over absolute value of x times square root of x squared minus 1. Y equals 1 divided by parentheses absolute value of x times square root of, I think it was x squared plus 1 Whoops. Close parentheses. Let me make sure that's what I want. I think that's what I want. X squared minus 1. Okay. Okay, now if we've done things right, this should go on top of the red graph. Yes, it did. Okay. So there is the graph that we want. So that's the right graph, not the one I had over here. Now, how did I know that I needed to fix that? Well, let's look at it. I knew I needed to fix it because the characteristics weren't all lining up correctly for me. Now let's go back here to the bigger view. Notice that the original function is increasing everywhere it's defined, so the derivative must be positive everywhere it's defined. And the graph I had wasn't positive over here in this quadrant. Now it's going the right way. It is positive. The graph has vertical tangent lines right at these endpoints, so the derivative has asymptotes there, vertical asymptotes. Okay. The original function, when x is negative over here, is concave up, so the derivative is increasing. When x is positive over here, to the right of 1, more specifically on the right side here, the original function is concave down, so the derivative is decreasing. Okay, so that definitely looks better. Now we should be able to check this in our calculator. Let me show you something real fast. Let's see. Which one are we doing here? We're doing inverse secant. Okay, so maybe remind you something from your algebra class or trig class. If y equals inverse secant of x, or better off written as arc secant of x, then we know that the secant of y is x. Now we also have some restrictions. The original function for the inverse secant, again, if you look back at this picture here, the y's are for this are between, well, they're between between 0 and pi. But it can't be pi over 2. So it's actually from 0 to pi over 2. 0 is okay, but not pi over 2. And pi is okay. Okay, so those are the y values. And the x's, and just to say it, so the x's go from negative infinity to negative 1, and then from 1 to infinity. Okay? Now, well, secant of y is 1 over cosine of y. So, cosine of y is actually 1 over x. Y then becomes the inverse cosine of 1 over x. Now let's graph that and see if that looks like this is the right function. Y equals a cosine, arc cosine, of 1 over x. Notice that traced right over the blue graph, the lighter blue color. So that is the correct thing for both positive and negative. So now I can enter that in as inverse cosine of 1 over x. Okay. And the numerical derivative, And our answer for our derivative was 1 over the absolute value of the square root of x squared minus 1. Okay, so it's 1 over absolute value of x. Whoops, need to start parentheses around the denominator. Parentheses, absolute value of x times square root of x squared minus 1, close parentheses. The square root, close parentheses of the denominator. Now, if we've done this right, hopefully these should agree in the table. Now, this is giving us error messages in here. So let me go up to the table here. Start at, let's say, start at negative 3 and go up by 1, so let's say. Okay, so we see some. Okay, they agree there for some negatives, and they agree there for some positive. So it is agreeing at some of the values that we need. Right. Well, at all the values, actually. We only check some of them, but it actually agrees at all of them. Okay. And that is, did these graphs get out of whack? Yeah. This graph actually goes here. Yeah. Okay. Now, how about the inverse cosecant? Well, inverse cosecant, I think we have the right graph here. It's always defined, the y's only go from negative pi over 2 to pi over 2, but not 0. And the x's go from negative infinity to negative 1 and from 1 to infinity. We notice the original function is always decreasing, so the derivative is always negative, which is what we have here. This one I do have the absolute value on again, which is what I need. So the derivative of cosecant, inverse cosecant is derivative of cosecant of u evaluated at inverse cosecant. And this really should be here. Okay. So with that, we can set this up, and what we want is the derivative of secant u. Cosecant u is cosecant u cotangent u with a minus. Put the minus in the front or the top. The angle is cosecant inverse of x, or inverse cosecant of x, arc cosecant. And so that's angle. See, cosecant is adjacent, or it's a hypotenuse over opposite, so it's absolute value of x over 1 here. And we can read the angles off of that. It's the cosecant of the inverse cosecant, actually of the absolute value of x, really. So we get absolute value of x here. And this one does work out correctly again. Let's check it. In a similar manner to what we just did, the inverse cosecant is actually, turns out to be the inverse sine of 1 over x, which is very similar to how we solved that one just a minute ago. Okay, and then actually it's the same answer as before, but we insert, what's going on my screen here? But we're going to insert a -1. Okay, so that's going to go here. Okay, that looks good. Okay, and then if we look at our table, something's wrong here. Try this again. Something's going strange with my graphics. Okay, here I got it. Uh-oh. Oh, it's Y1 and Y2. That's why they're not matching. Something you got to watch out for, so make sure when you're doing your table, you either turn off Y1 or you scroll over and only look at Y1 and Y2 in the table. Okay, that's good. Now, notice there is something kind of interesting happening in the table here. And this does happen sometimes when you're doing checks. Okay. Notice that the original function, the correct answer is actually in Y3. Get all these on one line here. Okay. Y2 is an approximation. Something's off a little bit here. Oh, it's supposed to say inverse sine, not sine. All right, let's try that again. This is something going weird with my computer here. Bear with me, something is really going wacky with the graphics here, but my emulator, but I think I can get it to show me what I want it to show. Alright, that's right. Okay, that's what it's supposed to look like. Now, let's see if we get the right table going now. Now the tables are matching. Okay, so we do get a check there. Notice that? So that works out correctly. Okay, so this gives us the basic graphs here. Now, one thing I do want to notice is if you graph, let's graph this out. If I graph y equals inverse tangent of 1 over x, you get, well, it's trying to connect the pieces, but you get a piece down here and a piece up here. And in Graphmatica, if you type y equals a cotangent of x, you're going to get basically the same thing. Okay? But this is not the way I define inverse cotangent. So if we're going to check this in our calculator, we've got to do something a little bit more complicated by making a piecewise defined function. I'm just not going to mess with that at the moment. But we saw that the graph did have the correct features that we wanted. Okay, so anyway, that took us a little bit of time to get through that, but now we have derived all of these formulas. Now let's take a look back at them for just a minute and then correct this one. I'm having problems with my computer working right. That should have absolute value. Okay. But with that said, look at all the ones that start with co are exactly like the ones that don't start with co, except they have a minus on them. And there is kind of a reason for that. Because you can look at the graphs. If you look at the graph of arc sine and arc cosine, if you flip the graph of arc sine upside down and then move it up a little bit, you're going to get the graph of arc cosine. Okay? So because of that, its derivative, moving it up or down doesn't change the derivative, right? So if we just flip this upside down here and did the opposite of arc sine, it's going to have the same shape and the same derivative as the arc cosine, which means that these two derivatives are just upside down from each other, which makes sense, hence the negative here. Same relationship is going to hold for arc tangent and arc cotangent. Take a look at the graphs there. If you take the graph of arc tangent, flip it upside down, and then shift it up some, you're going to get the graph of the arc cotangent. So that the shifting, again, vertical shift doesn't change the derivative. So the derivative, since it's flipped upside down on the shapes, the derivatives will be flipped upside down, hence the negative. And finally, same relationship here. If you look at the graph of the arc secant and then flip it upside down, you get the graph of the arc cosecant with the appropriate amount of shift and vertical shift. And so the two derivatives will just be opposites of each other. They'll be flipped upside down for each other. So we have some nice geometric relationships there. Okay, and so there are your rules. So the derivative of arc sine is 1 over square root of 1 minus x squared. The derivative of arc cosine is minus 1 over square root of 1 minus x squared. Derivative of arc tangent is 1 over x squared plus 1. Derivative of arc cotangent is minus 1 over x squared plus 1. Derivative of arc secant is 1 over x times the square root of x plus x squared minus 1, absolute value of x, I should say. And the derivative of the arc cosecant is minus 1 over absolute value of x times the square root of x squared minus 1. And then things work out quite nicely there. Let me try one more time, see if I can fix this absolute value where it's supposed to be. I'm not going to be able to get it done right now. I'll have to work on that later. Okay, I think